Okay, there's a quiz coming up next class, and for those of you that were a little bit lost with what was happening last class, I wanted to just make a quick tutorial video of some of what the most important things were from the last class. So, no tricks. I am not going to be emphasizing the acceleration equation. That one's not going to be on there, which means this guy is not going to be on there, which probably means this term of this equation will not be on here. So what mostly we'll be looking at, I'll just leave those back there for now, which means this will not be here, which means mostly what we will be looking at is we'll be looking at velocity, the definition, the change in position. We'll be looking at this equation, which is essentially an alternate form of this. And then maybe we'll look at one of these if we have a little bit of time. And then the other element that will be emphasized a lot is we also have to keep track of these graphs, these position versus time graphs. So what's going to happen in this video? We're going to do two things. First, we're going to go over a basic velocity versus time graph, the most basic. Then we're going to go over the delta x over delta t situation. Then we're going to go off and just look at what happens when we combine the two of them together. And that's going to be the substance of our quiz in the next class. So let's get started. First, position versus time graph. As we've seen a bunch of times before, we have position in a unit of distance, and we have time in a unit of time, meters and seconds in this case. We had three scenarios on the track when we ran around laps, and so we're going to do all three of those scenarios. The first scenario is we're going to accelerate slowly. Then we're going to go at a constant velocity. This is going to be a perfectly straight horizontal line. And then we're going to go flat, and we'll see what that means in a second. And then after that, we're going to go back to where we started. So we can break this graph up into 1, 2, 3, 4 discrete regions. Let's start with this one because it's the easiest one. So many of you will remember from class and from our notes and from the reference sheet that is posted in Google Classroom that when a position versus time graph is flat, we call it the flat top case, 90s hairstyle. The flat top case, do you remember what it means? Just check for yourself before I tell you. It means that the position is constant, but that's fancy. Why say it in the fancy way? It means that it's not moving. And we'll return to this once we'll do our 4 scenarios here. We'll do a scenario here, and then we'll return to these 4 scenarios in a second. So a flat top means that it's not moving. And the way that we can tell that is, let's say that someone ran to the 100 meter mark from 0 meters. Now, let's suppose it took them 10 seconds, which is too fast, but we'll roll with it. Speed demon, 10 seconds. Then they waited there for 5 seconds. This means at 11 and 12 and 13 and 14 and 15 seconds, their position was 100, 100, 100, 100. And if we were to draw a sort of T-chart of the position, the time and the position, it would be rather boring. 10 seconds, 100 meters. 11 seconds, 100 meters. 12 seconds, 100 meters. Nothing's happening, nothing's changing, there's no velocity. Great. So that's our first case. We'll leave that in orange. The orange case is constant velocity, the flat top case where nothing is moving and the position is not a function of the time. Great. The next example is the example of the slanted line, this line like this. And here we see that the position is changing. The position is changing as time passes. And we're going to go ahead and say that this is 5 seconds. My scale's a little off here. 0 seconds, 5 seconds, 10 seconds. From 5 seconds to 10 seconds, this straight line, this is a horizontal line right here, and this is a diagonal or slanted line, means constant velocity. Good. So we'll return to that in a second. Similarly, this is a constant velocity too. This is also constant velocity. It just happens to be constant velocity going down, going in the negative direction. We had a sleeper agent, a secret mission of a student who ran backwards when we ran the race. This is that example. That student is starting at we're starting at 100 meters, and as time passes, we're coming back towards 0 meters. That means we're going to have a negative velocity. So you know what? Why don't we just do that? We have a constant positive velocity here, and then the diagonal line in the red case is a constant negative velocity.